Welcome to Atomic Structure. In the Atomic Structure unit, we're going to look at chapters 2 and 7. From chapter 2, we're going to focus on some early models of the atom, and I'm hoping that some of this rings a bell. This shouldn't be the first time that you're hearing the name John Dalton. John Dalton was one of the first scientists to record data and do experiments to kind of focus on the structure of matter. From his experiments, he came up with some early theories. Now, theory is something that seemed to make sense at the time with the data available. But as new data is discovered, theories can change. What we go through is still considered all atomic theory. Even when we start looking at these quantum mechanical models, this modern atomic theory, this could change as new data is discovered. Now, some of this still seems to make sense. Atoms are made of matter is made of tiny particles called atoms. I'm cool with that. Atoms of a given element are identical. Atoms of different elements are different. Well, I have no problem with the second half. Yeah, atoms of different elements are definitely different. But are you kind of bothered by the first half now? Atoms of a given element are identical. What about isotopes? What about isotopes? Isotopes are atoms of the same element, but they have different masses because they have different numbers of neutrons. This first part today would not be true anymore. We have better data that supports the existence of isotopes. The rest of this I'm fine with. You can form compounds by joining atoms of different elements. A given compound must always have the same number of elements in the same ratio. So, for example, if you have a molecule of water, you have to have the same elements, hydrogen and oxygen, in the same ratio, 2:1. Anything else is not water. And chemical reactions involve a reorganization of atoms. I'm fine with that. The atoms themselves are not changed. That would be a nuclear reaction, which we are not concerned with at this point in the game. So now from these theories, as we experiment more, we can list 3 laws. A law is something that stands the test of time. These laws have not been proven wrong, although I always have somebody that thinks they have broken the law of conservation of mass in the lab. In a chemical reaction, mass is neither created nor destroyed. So the mass of your products should be the same as the mass of your reactants. Now, obviously, that doesn't always happen in the lab because of errors. The law of definite composition says that a particular compound will always have the same proportion of elements by mass. So, for example, if I have water, H2O, if I were to calculate the percent composition of hydrogen and oxygen, that should always be the same. If the composition is definite, it means it's not changing. If water always has 2 hydrogen and 1 oxygen, it should have the same percent composition by mass. Although we can join the same elements in different ratios. That's the law of multiple proportions. This is a wordy definition for the law of multiple proportions. I just think of it as you can join the same elements in different ratios. But be aware that the existing compounds then will have different properties. Water and hydrogen peroxide do not have the same properties. If you've ever had to gargle peroxide, if you have your wisdom teeth out or something like that, it's not refreshing. I wouldn't grab the hydrogen peroxide after a good workout. No, it's real different. It's kind of fizzy. It's awkward. You wouldn't want to drink it. Other early experiments that I'm hoping are familiar to you are this J.J. Thomson cathode ray tube experiment. This is where we enter in the electrons. J.J. Thomson had this glass tube filled with a gas. The gas was hooked up to an electrical current, and it kind of glowed like a laser beam. They called it a cathode ray. Now, previously we thought that atoms are just these tiny little particles and there was nothing else to it. They're neutral particles, so they should not be affected by any kind of an outside electrical field. So he took a positively charged plate and a negatively charged plate. And he figured that the laser beam should just glow in a straight line, no big deal. And boy, was he in for a surprise. The beam was bent. This beam of particles was attracted to the positive field and repelled from the negative field. Here's where we start entering in the idea of negative particles that make up an atom. Call them an electron. There must be some negative component to an atom that's attracted to that positive field. Now we know even more that the electrons are on the outside of the atom. This electron cloud is on the outside of the atom. So yeah, it should be attracted to a positive field. So the idea of an atom changes a little bit now. Instead of it just being this tiny little particle, that's all there is to it, we're going to put subatomic particles into play. Now, he didn't really know what to do with these electrons, so he just said, I don't know, maybe there are these negative little electron particles, and we'll scatter them throughout the atom. I don't know. Now, since an atom needs to be overall neutral, there must be some positive component to an atom as well, but he didn't really have any data to support the exact structure of this positive material. So he said, I don't know, maybe these electrons just kind of swim around in some kind of a positive background material. I don't know. This was called the plum pudding model of the atom, where the electrons are like little chunks of plum, and the pudding is like the positive material. If you've ever had plum pudding, it's not the greatest. I had a girl try to make it one time. I don't know if she thought it was going to get her bonus points or whatever. It was disgusting. Now maybe it was just a bad recipe or a bad chef, but it wasn't my favorite. But I do kind of think about this idea of maybe like a chocolate chip cookie, where the chocolate chips are the electrons and the cookie is like the positive material. We don't really know exactly what it looks like. But at least now I have neutral atoms. Another experiment that focuses on electrons was the Millikan oil drop experiment. Now, we know that electrons are negatively charged. This Millikan oil drop experiment will give us the exact charge on an electron. How negative is an electron? Here's kind of the setup. So he's got this contraption, for lack of a better term, and obviously we need some oil. So he's got this sample of oil, and it's almost as if he kind of sprays it in a real fine mist, as if it were like in an aerosol can or something like that, where we can spray a fine mist of oil droplets into the upper chamber of this contraption. Gradually, those oil droplets will fall through this little hole into the bottom part, where we're going to have an X-ray source. Now, these X-rays are going to ionize the air in the bottom chamber, which really just means that they're removing electrons. The X-rays remove electrons from atoms in the air, oxygen, nitrogen, all that good stuff. Now, some of these oil droplets are going to pick up the electrons and become negatively charged oil droplets. Ooh, that sounds exciting. Okay, so here's what happens now. He can charge these two plates. So we've got this upper plate with a positive charge and the lower plate with a negative charge. He can adjust the charge to kind of play with these oil droplets. So he looks through this microscope, and I've got these negatively charged oil droplets. if he increases the charge on the positive plate, opposites attract. So he can get these negative oil droplets to kind of attract or rise up toward that upper positive plate. Sometimes he can adjust the voltage so that these oil droplets can kind of suspend right in the middle of the two plates. Now, by looking at how much he needs to adjust the voltage, and also taking into consideration the mass of these oil droplets and some physics, which would be kind of exciting, but we won't go into these physics equations, he determined that the charge on these little oil droplets was a multiple of this. About 1.6 times 10 to the negative 19th coulombs. A coulomb is just a unit of charge. We'll look at coulombs again at the end of the year when we talk about some electrochem. Just a unit of charge. Now, some oil droplets maybe had 2 electrons, 3 electrons, 4 electrons. And so he could kind of figure out by looking at how much he needed to adjust the voltage to make these little oil droplets rise and fall between the positive and negative plates, that the voltage applied was always a multiple of this 1.2 times 10 to the negative 19th coulombs. This number is not anything that you need to memorize. It's in the AP packet. It's under a section called atomic structure. It's listed as electron charge, and it has it listed as negative 1.602 times 10 to the negative 19th coulombs. The charge on one electron. Now here's kind of a visual if you're a visual person.
1909, Robert Millikan, working at the University of Chicago, succeeded in measuring the charge on the electron. He allowed a fine spray of oil to settle through a hole into a chamber where he could observe their fall. The top and bottom of the chamber consisted of electrically charged plates. He introduced a source of X-rays which can cause creation of charges when they strike matter. Charges produced by the X-rays attach to an oil droplet, producing one or more charges on the droplet. When there is no voltage applied, the fall of the droplets is determined by their mass and the viscosity of air through which they fall. When a voltage is applied, the droplets that have a negative charge will fall more slowly, stop falling, or even rise, depending on the number of charges on them. By adjusting the applied voltage and observing the droplets both with voltage off and voltage on, Millikan was able to determine that the charges on the droplets were all multiples of the smallest value, 1.6 times 10 to the minus 19th coulombs. He took this to be the charge on a single electron.